The first warning was not a sound. It was a number. On February 27, 2026, during a routine roll maneuver, Voyager 1's power levels dropped further than they should have. And engineers at JPL realized within minutes that the spacecraft was within fractions of a watt of tripping its own undervoltage fault protection, a self-preservation reflex that could have ended the mission permanently. They began drafting recovery commands immediately, but the commands had to travel 23 hours through interstellar space to reach the probe. By the time anyone on Earth knew there was a problem, whatever was going to happen had already happened a full day earlier. They were not saving Voyager. They were waiting to find out if it had already saved itself. They were watching a ghost of an event that had already concluded, scrolling across their monitors while the real spacecraft drifted through interstellar space, either alive or dead, and there was no way to know which until tomorrow. Wherever you are watching from, whatever time it is in your part of the world, sit with that for a second. The most distant object humanity has ever built is fighting for its life right now, in real time, on a 22-hour delay, and almost no one is talking about it the way the data demands. In April 2026, NASA sent another command sequence. This one shut down the low-energy charged particles experiment, an instrument that had been operating almost continuously since 1977. 49 years of unbroken science ended with a single transmission. The press release framed the decision as extending the mission. The phrasing was careful. The phrasing was also wrong in a way most people missed. 7 of Voyager 1's 10 original instruments are now dead. 2 science instruments remain. That is not extension. That is amputation performed to keep a heart beating for a few more seasons. Voyager is not exploring anymore. Voyager is dying, and we are watching it die in 22-hour delayed slow motion. By the end of this, you will understand what the final signal will technically be, when it will arrive, what it will actually mean, and why there will probably not be another one in your lifetime. But to understand what we are about to lose, you have to understand what Voyager actually is. And the official version of that story is wrong in a way most people never notice. You already know the romantic version. Launched in 1977, the grand tour of the outer planets, Jupiter, Saturn, Uranus, Neptune. The pale blue dot photograph that taught a generation what their planet actually looks like from beyond the rings of the gas giants. The golden record, plated in gold, containing greetings in 55 languages, music from Bach to Chuck Berry to Blind Willie Johnson. The sound of thunder, the sound of a mother kissing her child. Voyager became, in the public imagination, humanity's ambassador to the stars, a machine that would travel forever. Forever is doing extraordinary work in that sentence. Here is what is actually true. The spacecraft itself will travel essentially forever. There is nothing in interstellar space to stop it. No friction, no atmosphere, no gravitational well strong enough to capture it. Voyager 1 will keep moving for billions of years. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445, currently drifting through the constellation Camelopardalis. The golden record will outlast every human civilization that has ever existed, and probably every human civilization that ever will exist. But the spacecraft is not the signal. The signal is a radio transmission generated by a small radio transmitter powered by a slowly cooling lump of plutonium. And that radio has a hard expiration date, measured not in millennia, but in years. Strip the spacecraft of the radio, and you strip the spacecraft of meaning. What continues afterward is metal in motion. Beautiful, historic, but mute. This is the part the public framing softens. Voyager is not really a message to aliens. The probability that any intelligent species ever encounters it is so small, it functionally rounds to zero. Voyager is a message to ourselves, and the messenger is about to go silent. For reasons that have nothing to do with distance and everything to do with the physics of a 49-year-old nuclear battery losing roughly 4 watts of power every year. We have been here before. Pioneer 10 launched in 1972, Pioneer 11 in 1973. Both carried plutonium hearts. Both sent signals home for decades. Both went quiet. Pioneer 11's last contact was in 1995. Pioneer 10 transmitted for the final time in January 2003. Most people watching this have no memory of either silence. There was no televised farewell, no moment of national reflection, no primetime documentary. The most distant objects humanity had ever built simply stopped responding, and the public did not notice, and the press largely did not cover it, and within a year, the silence felt as if it had always been there. Just a final faint pulse, and then nothing. Voyager's death will look the same. Read that carefully. The 2 spacecraft that pioneered interstellar flight died without anyone outside the mission team paying real attention. That is the precedent. That is the template. To understand why this spacecraft is dying, you have to understand what is actually powering it. And it is not what you think. There are no solar panels on Voyager. There could not be. At its current distance, more than 25 billion kilometers from the Sun, sunlight is so weak that any solar array large enough to power the spacecraft would be the size of a small office building, and even then it would barely register a charge. Voyager runs on something different, a radioisotope thermoelectric generator, an RTG. The mechanism is brutally simple. A brick of plutonium-238 decays. Decay produces heat. Heat flows across a thermocouple. The thermocouple converts the temperature difference into electricity. No moving parts, no batteries to recharge, just nuclear warmth slowly bleeding out into space. Plutonium-238 has a half-life of 87.7 years. That sounds like a long time. It is not. At launch in 1977, the RTG produced roughly 470 watts, less than a hairdryer. Today, after 49 years, it produces roughly half that and falling. The decline rate is about 4 watts per year. 4 watts is the wattage of a small nightlight, a single LED bulb in a hallway. Every 12 months, that is what gets subtracted from the entire power budget of the most distant machine humanity has ever built. Now here is the part that should bother you. The decline is not just the plutonium decaying. The thermocouples themselves degrade. The materials that convert heat into electricity get worse independently of the fuel. The plutonium is doing its part. The hardware around it is not. Voyager is losing power faster than the half-life curve would predict. The plutonium is not the bottleneck. The conversion hardware is. A spacecraft engineered for a 4-year mission is now running on hardware operating decades past every conservative estimate of its useful life. Think about what that means for the engineers. They cannot add power. There is no plug, no battery swap, no docking port, no second stage anything. There is only the slow, inexorable cooling of a metal cylinder 25 billion kilometers from the nearest human being. This is a 49-year-old machine running off a dying nuclear pacemaker, an unimaginable distance from any possible repair. And the power problem is bad. But the power problem is not the worst problem. The worst problem is what happens when the available power drops below a specific, very low threshold. Because at that point, NASA loses the ability to do something most viewers never even think about. They lose the ability to keep Voyager pointed at us. Voyager does not just need power to run instruments, it needs power for heaters. Tiny electric heaters that keep the hydrazine fuel lines from freezing in interstellar cold. Those fuel lines feed the thrusters. The thrusters fire in tiny pulses to keep the spacecraft oriented correctly. And the orientation matters because of one specific thing. The high-gain antenna has to point at Earth. If the heaters fail, the fuel freezes. If the fuel freezes, the thrusters fail. If the thrusters fail, the spacecraft begins to drift, rotating slowly on its axis, the antenna sweeping across the sky like the second hand of a broken clock. The transmitter will still be running, the radio will still be broadcasting, but the signal will no longer be aimed at us. It will be aimed at empty space. The signal will not end. It will just stop arriving here. Voyager will keep talking. We will simply no longer be in the room. This has been an open secret in the Voyager community for years. In 2023, residue from decades of thruster firings began clogging the original fuel lines. The team switched to backup thrusters that had not fired in nearly 4 decades. They worked, barely, and there is no third set. The team has a plan for what comes next. They call it the Big Bang. It is the most aggressive power conservation strategy they have ever attempted. Rather than turning off one component at a time, the Big Bang would swap out multiple power-consuming systems all at once, trading older components for lower power alternatives. Tests are planned on Voyager 2 first, in May and June 2026, because Voyager 2 has slightly more power to spare and is closer to Earth. If those tests succeed, the same procedure will be attempted on Voyager 1 no earlier than July. If it works, NASA might even be able to turn the LECP back on. If it does not work, the team may lose the spacecraft outright. One bad command, executed 23 hours later by a machine they cannot physically touch, and the mission ends. There is no rollback. There is no second attempt at first contact. Whatever happens after that command executes is what happens, forever. Imagine writing code for a patient you cannot examine, cannot reach, cannot rescue. Imagine pressing send and waiting nearly a full day to find out whether you saved them or killed them. That is the daily reality of the Voyager team in 2026. And even if the Big Bang works, even if it buys another year, there is something most people do not realize about the signal itself. It is not what it used to be. People assume the problem with talking to Voyager is distance. That is the intuitive answer. The spacecraft is far away, so the signal is weak, so eventually we cannot hear it. That is not exactly wrong, but it is not the real problem. The Deep Space Network can still hear Voyager. The signal that arrives at the world's largest radio dishes is about 10 to the power of -18 watts, a billionth of a watt. Less energy than a single snowflake delivers when it lands on a leaf. And yet we can detect it, with hours of integration time, with software designed to fish a coherent signal out of cosmic background noise, with antennas the size of office buildings, cooled, calibrated, and aimed with extraordinary precision. We can still hear Voyager. That is not the problem. The problem is what the signal can carry. Voyager's data rate is now 160 bits per second. Read that number carefully. Not megabits, not kilobits, bits. 160 of them per second. For comparison, the slowest dial-up modems of the 1990s were 56 kilobits per second, about 350 times faster than the data rate of humanity's most distant spacecraft. A single low-resolution photograph would take days to transmit. A second of audio would take longer than a feature film to send. Now think about Apollo. In 1969, astronauts streamed live television from the surface of the moon. Grainy, ghostly, but live. Voyager, at roughly 11,000 times the distance, can barely send a sentence per minute. The math breaks the fantasy. It is not that Voyager is too far away to talk to. It is that the conversation has become so slow, it is no longer a conversation. It is a letter being mailed one syllable at a time. And the signal is going to slow further. As power declines, transmitter strength drops, the encoding becomes more conservative, and the bits per second number creeps lower. The signal is not just thinning, it is narrowing. The bandwidth of the most distant conversation humanity has ever held is shrinking month by month, and there is nothing the team can do to widen it back. Each year, fewer words can cross the gap. Each year, the spacecraft has less to say and less ability to say it. This is the technical layer, this is the physics. And the physics is harsh enough. But the human layer is worse. Because the people who designed Voyager, the people who knew this machine in their hands and in their sleep, are leaving too. Voyager was designed in the late 1960s and early 1970s. Its onboard computer architecture is older than the personal computer. The flight software is written in assembly language for a processor that has not been manufactured in decades. There is no Stack Overflow for Voyager. There is no documentation hosted on a wiki. Much of the original engineering knowledge exists only in the memories of the people who were there, and in some cases, on physical paper. Notebooks, printouts, hand-drawn diagrams, margin notes in pencil. Some of the most critical operational knowledge about this spacecraft exists only as ink on yellowing pages in a filing cabinet in California. In 2024, when Voyager 1 began returning garbled data, the team that solved the problem included engineers who had been pulled out of retirement. They were the only ones left who understood the relevant subsystem. They read documentation that exists nowhere in digital form. They worked the problem for months. They fixed it, and then most of them went back home. Today, the team that maintains Voyager is roughly a dozen people. Many are in their 60s and 70s, some are older. The control room at JPL is not a futuristic command center with glowing screens and holographic displays. It is offices, with old monitors, with paper printouts taped to walls, with engineers who learned this machine when they were young and who are now the last people on Earth who can speak its language. Imagine your grandfather is the only person alive who can read a particular handwriting. When he dies, no one else on Earth can read it. That is Voyager's documentation problem. Imagine learning to drive a car whose manual is written in a language no one teaches anymore. That is what it means to debug Voyager in 2026. The spacecraft is not just running on dying hardware, it is running on dying human memory. Compare this to the Apollo guidance computer. Its source code had to be rediscovered decades after the missions ended and rehosted on GitHub by hobbyists who reverse-engineered the original printouts. That recovery happened only because Apollo was over. The spacecraft were in museums. Voyager's situation is worse. The spacecraft is still operating. The team still needs to send commands. The knowledge is not just historical, it is operational. It is being used right now. When the last engineer who knew Voyager retires, something will be lost that we did not plan to lose. A line of human continuity stretching back to typewritten memos from the Nixon administration will end. But the deeper problem is what happens after Voyager goes silent. Because we have no replacement coming. There is no mission currently under construction to replace Voyager in interstellar space. None. The interstellar probe concept exists. Studies have been published, mission architectures have been sketched, but nothing is being built. Nothing is funded for launch. The most realistic estimates suggest a successor would take roughly 15 years to develop and launch, and then another 50 years to reach Voyager's current position. Add those numbers. 65 years from a green light. Even if a replacement were approved tomorrow and launched on schedule, the first new data points from beyond the heliosphere would arrive after most people watching this video are dead. Now think about the fuel. Voyager runs on plutonium-238. The United States stopped producing it in 1988. For 25 years, the country that put the Voyagers into deep space made no new Pu-238 at all. Limited production restarted in 2013, but the numbers are modest. Current annual production is measured in hundreds of grams. A Voyager-class mission needs kilograms. There is not enough fuel in the national stockpile to build another Voyager, even if we wanted to. The supply problem alone would delay any serious deep space mission by years. Then the economics. Voyager cost roughly $865 million in 1970s dollars. Adjusted, that is around $4 billion today, and a modern equivalent would almost certainly cost more, take longer to develop, and require political continuity across multiple presidential administrations and congressional sessions. That kind of continuity is something the modern American political system has not demonstrated in decades. A mission whose first data point arrives 65 years after approval is not a project. It is a generational covenant. And we are no longer a civilization that signs those. Then the infrastructure. The deep space network, the array of antennas that listens to Voyager, is itself aging. Some dishes are over 60 years old. Maintenance is constant. Upgrades are slow. And bandwidth is being divided across a growing list of distant missions. Voyager is no longer the priority. It is one signal among many, and it is the quietest of them all. This is not a "we will send another one when we feel like it" situation. This is a generational gap. The conditions that produced Voyager in 1977 do not exist anymore. The fuel supply, the political consensus, the unified scientific ambition, the infrastructure, the patience for a half-century mission, most of those have eroded. Some have collapsed. And the institutional explanation for all of this, the way it gets discussed in official language, is the most quietly damning part of the entire story. Read NASA's recent statements about Voyager carefully, not for what they say, for what they choose not to say. Extending the mission is the phrase used for amputating it. Power conservation is the phrase used for turning off the instruments that defined the mission's scientific value. Operating into the 2030s is the optimistic framing, often quoted in headlines. The realistic framing, at the current decay rate, is that even the radio transmitter itself, not the instruments, the radio, may go dark in the early 2030s. The mission may end not when there is nothing to broadcast, but when there is no broadcaster left. Why is the language softer than the physics? Because NASA needs public goodwill to justify future deep space missions. A spacecraft still going strong at 49 is a better headline than "Spacecraft slowly dying as we fail to fund replacement." The Voyager team genuinely loves this spacecraft. They are not lying. They are protecting a story that protects future science. Let me be fair here, this is not a conspiracy. The engineers are doing extraordinary work. The communications team is not misleading anyone. They are choosing which truth to lead with. The data is all public. The instrument shutdowns are announced. The power decline is documented. Nothing is hidden. But the truth they lead with is the comforting one, and the public has stopped asking what is behind it. This is what institutional softening looks like when it is done by people who care. It is not deception, it is curation. It is selecting which true sentence to put in the headline and which true sentence to put in paragraph 7. And the result, accumulated across years of press releases and interviews, is a public perception that does not match the engineering reality. The story most people carry in their heads about Voyager is a story from the 1990s. The actual spacecraft is in 2026. Voyager is not in trouble because NASA failed. Voyager is in trouble because physics is winning, because plutonium decays, because thermocouples degrade, because thrusters wear out, because engineers retire, because national priorities shift, because Pu-238 production was suspended for a generation, because political continuity is harder than physical persistence, because we, as a civilization, did not plan well enough for the day this would happen. And the day this would happen is now. Which raises the question almost no one asks. The question the headlines avoid, the press releases sidestep, the engineers will not state plainly. What is actually inside that last signal when it finally arrives? The final transmission will not be a sentence. It will not be a goodbye. It will not be a Carl Sagan monologue echoing across the void. The last signal from Voyager will be a stream of engineering telemetry. Temperature readings, voltage levels, magnetic field data, plasma wave measurements. Numbers, just numbers, until they stop. That is what 49 years of human ambition will sound like at the end. Not music, not poetry, just a column of decimal values recorded by a half-asleep engineer at a console in Pasadena, the last one of which will not be marked at the time as the last one. No one will know it was the last until days, maybe weeks later, when no successor packet arrives. The death will be recognized in retrospect. There will be no moment, only an absence that slowly hardens into certainty. Now think about what that actually means. The last signal will be the last data point humanity ever receives from a working instrument outside the heliosphere. After that, our knowledge of the local interstellar medium goes static, frozen at whatever the final transmission tells us. For an unknown number of decades, possibly centuries, until a successor is built, launched, and arrives at a comparable distance. We will have crossed a threshold we cannot uncross. We will have lost real-time eyes beyond our own star. For 49 years, humanity has had a continuous data stream from beyond the solar system. That stream is older than the modern internet, older than most countries' current governments, older than most of the people watching this. There are adults alive today who have never lived in a world where Voyager was not transmitting. When that ends, we become a civilization that used to have eyes outside its own neighborhood and now does not. We become a civilization that had a window open and let it close and did not build another. And here is the deeper layer. The golden record will continue. Voyager itself will continue. The spacecraft will physically reach the vicinity of Gliese 445 in roughly 40,000 years. But we will not know. We will not hear about it. From our perspective, the story will end mid-sentence and continue silently for 40 millennia. Voyager's longest journey will happen entirely outside human awareness. The most ambitious thing our species has ever made will spend the overwhelming majority of its existence carrying our message into the dark without anyone left to follow it. This is not the death of a spacecraft. This is the closing of a window we did not build a replacement for. Which leaves one final question, the only one that actually matters now. When the signal goes quiet, what should we do? Look at the evidence one more time, compressed. 7 of 10 instruments dead, 4 watts of power lost every year with no mechanism for adding more. A 23-hour command delay between Earth and the spacecraft. No successor under construction. Not enough plutonium-238 in the national stockpile to build a replacement. A team of roughly a dozen aging engineers maintaining a machine no one fully knows how to rebuild. Each of those facts, taken alone, is a problem. Taken together, they are a verdict. The illusion most people still carry is that Voyager's silence will be a sad but inevitable moment of national reflection. A Carl Sagan tribute reel, a quiet thread on social media, a tasteful press release with a photograph of the pale blue dot, a few thoughtful op-eds, and then the news cycle moves on. That is the comfortable version. That is the version the public framing has been preparing for. The reality is harder. The signal will not just stop. It will stop and not be replaced, possibly for the lifetime of everyone watching this video. The silence will not be a single moment. It will be the start of a generational gap in human knowledge that we are currently choosing not to close. Choosing through funding decisions, choosing through plutonium production levels, choosing through which missions get approved and which stay on paper. Choosing through what we, as a public, are willing to demand. Go back to the opening image. February 27, 2026. The roll maneuver, the power drop, the engineers staring at a 23-hour-old warning, waiting to find out whether the spacecraft had already saved itself or already ended itself. At the time, it felt like a near miss, a scare, a close call. It was not. It was a preview. It was the shape of the actual ending, sketched out in miniature, with a temporary reprieve attached. The real ending will look exactly like that day, except no signal will come back the next morning to tell us everything is fine. Let me be fair, one last time. This is not about blame. NASA is not the villain. The engineers are not failing. The science is not lying. The physical reality is simply harsher than the comforting public framing, and we as a civilization made choices whose consequences are now arriving on a 22-hour delay. And here is the narrow hope, allowed only now, only after the warning has fully landed. The Big Bang procedure could work. It could buy years. The interstellar probe concept could move from paper to construction if the political will appears. A new generation of engineers could learn Voyager's language before the last one retires. The plutonium stockpile could be rebuilt. None of this is impossible. All of it requires choosing it. All of it requires us to act as if 65-year missions still matter to a civilization that increasingly thinks in quarters. When the last signal arrives, and it will arrive, the question is not what it says. The question is whether anyone will be listening, whether anyone will understand what it meant, whether we will have built anything to take its place, whether the silence that follows will be the silence of a civilization that ran out of curiosity, or the silence of a civilization that simply got distracted at the wrong moment in its own history. Right now, the answer is no. Right now, the silence is the choice we are making by not making any other choice at all.